or a quench hardening process. Steel rods are heated in a furnace to 850 degrees Celsius and then cooled in a water bath to an average temperature of 95 degrees Celsius as shown in the figure. The water bath has a uniform temperature of 40 degrees Celsius and a convection heat transfer coefficient of 450. So they're giving us the H already. If the steel rods have a diameter of 50 mils and a length of 2 meters, determine the time required to cool the steel rod from 850 to 95 in the water bath, and the total amount of heat transfer during the quenching of the steel rod in the water bath, assuming that the thermal properties of the steel are constant and that the system is a lump system. So heaps of things for us to talk about here. First things first, what the hell is a quenching process? If you guys did 205, you learned about this. It's the process that we get steel and make it stronger, harder, that's the proper way to say it, by quenching. So we take it from a high temperature into low temperature, and that makes it so much harder that we actually have to do a process afterwards to make it a bit softer, or else it breaks in service. So it's a process to make steel stronger. Note that we have a new thing here, which is the time component, and we haven't talked about time component so far. We never really worried about how much time things took. So this is going to be new. The other thing, lump system. Do you guys recall what a lump system is from your lectures? That's actually a perfect explanation. What Georgie is saying is that, for instance, let's say that this guy is at 25 here. This is the rod, by the way. Okay? Rod. Horrible drawing of a rod. Let's say it's all at 25, and then I take a match and I light it up and I put fire here. So what will happen is that this guy here would increase the temperature. Let's say it's now at 70, but now because this is at 70, then this guy will be at 65, and it'll be at 50, 45, all the way. It's going to trickle down because we know the conduction effect is going to go. Well, if it's a lump system, what this is saying is that whenever this becomes 70, the whole thing becomes 70 straight off the bat. So if it changes its temperature, the whole thing changes its temperature. We're not going to have, it's inside the same solid, we're not going to have different situations going on. That's what the lump system means. So heat is coming from the outside in, and it's changed, so it's not happening from inside of the body. And then we're saying that when he enters through the whole thing, and it's uniform throughout the whole thing. And that's a very good assumption depending on the situation. For instance, if you have a very large surface area in relationship to your volume, that's a good assumption. If your material is very conductive, thermoconductive, it's a good assumption as well. So depending on the delta T, depending on several things, it's not an unreasonable assumption. And for a quenching process of these rods, it's probably a good assumption. That's what the lump system means. What else? So these are the highlights that I was talking about. What else? We are assuming a uniform temperature of 40 for the water. You can see the 40 over here. Now, what this is saying is kind of the same thing as before. This is T infinity, right? There's a lot more water than there are steel rods. So it doesn't matter whether we're quenching it from 850 to 95, whether we're doing 1, 2, 3, 100 rods, there's way more water than the rods. So the temperature leaving the rod into the water is not going to change the temperature of the water. So in other words, our T infinity, I should say T water equals T infinity, right? So that's 40 Celsius. What else? I think that's it for now. Now, what I want you guys to do is I want you guys to attempt to do part 2, because part 2 is something that's we did it before. You guys are comfortable with it. There's no novelty there. So what we're saying is we're taking this rod and we're going from 850 Celsius down to 95. Was it 95? Correct me if I'm wrong. And if this is the case, how much energy needs to leave this rod? What's the Q that needs to leave? Energy, not energy rate, energy. How much energy, joules, do we require to leave this rod so that we can have this change in temperature for the rod? All right, so we know that we've talked about this refers back to week 2, right? So that's why I said you guys would be very comfortable with it. And this refers back to, C sub P, heating capacity. We talked about how that works, joules per kilograms per Kelvin. So if I multiply that by the difference in temperature that I'm trying to achieve and the mass, I can get the amount of energy required, right? And then we have all this information except for the mass that we don't have, but we do know the density. And with the density, that mass becomes trivial because we know density is just mass over volume. So that means if I want to find the mass, all I need to do is multiply the density by the volume. So let's go ahead and find what is the volume of this guy. This is a steel rod. So if we take this area that I drew in blue, if you take this area and multiply by the length, I can get the volume of this rod, right? So it's the volume of a cylinder. So I'm going to do the volume will be my pi r squared times my length. My it's 50 millimeters, right? So 50 millimeters, so that's going to be 25 times 10 to the minus 3 squared, and the length is 2 meters. So this gives me, what did I get? I got this as 3.92 times 10 to the minus 3. 3.92 times 10 to the minus 3. Back me up if you get anything different. Let me know. And that's going to be meters cubed. So we're doing meters squared over here times meters cubed. So that means that my mass, I can go back to this one, my mass will just be equal to, what's the density for 7832? 7832 times the 3.92 times 10 to the minus 3. What I'm doing here is I'm multiplying, I have kilograms per meters cubed, and I multiply that by meters cubed, and that gives me a mass of 30.76, and that will be in kilograms. So great, this allows me to do this one here now. 30.76 times C sub P 434 for the steel rod. Again, just as a reminder, we know that this guy does change with temperature, but we're assuming a constant for the sake of simplicity for all this unit. And we're changing our temperature from 850 down all the way to 95. Could you have done the other way around, negative? You sure can. But you know from the start, from the very, very, very first start, we know that Q is leaving the rod and Q is going from my rod into my water. We knew that before we even did any equations, right? So whether you get positive or negative, it's just telling you the direction. This is, what did I get? 10.1 to the 6. Does that match what you guys got? Yep, and then unit-wise, we have kilograms for the mass. And then this guy here, this is in joules per kilogram per Kelvin. So joules per kilogram per Kelvin. And then we have a difference in temperature that it can be in Kelvin or in degrees Celsius. It doesn't matter. So this is in joules.
Sir?
Yes?
Did you multiply the volume by 2?
Did I multiply the volume by 2? No, I did not.
Okay, got it. Yep, that's the mistake I made.
I did not multiply it by 2. This 2 here is the length, right? It's not 2 pi r. Watch out, because we're not looking for the area, we're looking for the volume.
Yeah, the 2 pi r squared L.
Yeah, cool, good. Like I said, from the start, we knew how to calculate the amount of energy required to go from 850 to 95, right? Either way, if it's from 95 to 850 or 850 to 95, we know that this is the amount of energy that will be required to enter or leave this rod. Now comes the more interesting part and the more difficult part. How do we find the time? How do we find the time component? This is new. We never talked about time before. Well, I'm going to go over the integration to solve this problem. You don't need to integrate, all right? It's most likely, I've actually wrote down from a previous year that was on slide 7 of week 4. So you can go and use straight this equation. I'm going to show you how we get to this equation because this unit also has a lot of components of deriving and integrating. So if you're going for a HD, if you really want that high mark, you're going to be comfortable with how equations come to be because you're going to see that we're going to be looking at deriving and integrating equations as we go. So this is how this comes to be, all right? Because it's an interaction between the fluid and the solid, the assumption is that the whole energy leaving the rod and going into the fluid is going to be due to convection, okay? Convection is going to be the reigning heat transfer mode here. And convection Q dot respects Newton's law of cooling, which says it's equal to HA delta T. Okay, this equation is very simple, yet very powerful. This is the area through which there's heat exchanging. This is the convective coefficient, which takes into account what are the materials and all the things we're going to look into more details in the future. But we're given this in this problem as 450. And this delta T here, watch out, okay? This delta T here is a difference between the water and the steel rod, okay? So this, I can rewrite this delta T as temperature for the rod minus T infinity. Okay, now the problem is that this guy here is changing with time. This temperature changes time. It starts at 850 and it goes down all the way to 95. To account for that, we're actually going to use this equation here because we know that the amount of energy that this guy is absorbing or releasing has to be related to this, right? But note that this one here is in energy. This is an energy rate. So what I'm going to do is I'm going to derive both sides of this equation by the time. And then over here, what's going to happen is because this mass is a steel rod, it's not changing. It's not mass flow or anything like that. This is going to leave. It's not going to change with time. My C sub P is not going to change with time. although it should respect the temperature as we talked about before, we're simplifying, saying that it's not going to change whatsoever. But my delta T will change with time, and that's the catch, right? So this is going to be something like this. It's going to end up being like Q dot on the left-hand side will be mass C sub P, and then how my temperature is changing with time. Okay, that's my differential way. And I'm going to say Q equals Q, and this is going to give me the following. Minus H A T minus T infinity will be equal to the mass times my C sub P dt temperature dt time. And from here, I can do is, you can choose whatever you find best, but I'm going to leave dt on its own on that side there. And I'm going to have minus mass C sub P, H, A, and over here, I'm going to have dt, and this dividing by T minus T infinity. And now I can integrate, and I'm going to integrate from time 0, before anything happens, to my final time. And on this side here, I'm going to integrate from my initial temperature, that's the initial temperature of the rod, all the way to the final temperature of the rod. This integration here you can do by substitution. It's very straightforward. It's going to be the natural log of the substitution. And this integration renders the time will be equal to, all of this is not dependent on time, so you can leave the integral. So it will be equal to minus C sub P H A natural log of T final minus T infinity divided by T initial minus T infinity. Okay, and this is how we get to this point. That's all the assumptions that we just had. Why is the H negative in the beginning? Just the original equation? Yes, the original equation, and once again, to account for the fact that the gradient is always going from high to low. So it's always going from the highest temperature to the lowest temperature. That's why the negative is there. Same reason why it's there on Fourier's law. Okay, so guys, once we reach this point here, we are ready to crunch the numbers and find the amount of time required. There is another way this equation is written, okay, which is in respect to the temperature. So let's say you're not looking for the time, you're looking for the temperature. So what you can do is you can take e to the negative t, and then usually we do b. So we transform this whole thing into, it will be b to the minus 1, I guess. And then this is going to be equal to tf minus t infinity divided by ti minus t infinity. Okay, so if you're after the temperatures, you can also use this form here, and they plug in how much time is going to elapse. All right, we're after the time, so we are actually interested in using this form of the equation. So that means I can find my time by plugging in these numbers. We have everything we need. We can go ahead and find the time required. Okay, what is the mass? 30.76. What is the C sub P? 434. What is my H? 450. What is my area? What is the area of this steel rod? And there are multiple. You can answer this question different ways, and they can all be right. What is the area that I should consider there?
Sorry, I have a question. My internet cut out. Can I ask just one question from the beginning? Now, I understand the Q minus H times the area, but did you just multiply it by the dt to be able to differentiate it, or on what basis did you differentiate the equation?
I derived it here in the beginning in respect to time. So I took both sides of the equation in respect to time.
So yeah, okay, you differentiated both the side of the equation related to time, and that's it.
That's it, yes. And this gave me the heat flow, the rate of heat. And on this side here, because the mass and the CP came out, this just gave me dt. Yep, so I left it in the form of the derivative.
Yeah, okay, thank you.
Did you put boundary conditions, the TF and TI? The big T's are temperatures, right?
That's correct. The big T's are the temperatures. And here you don't have to put like this. It doesn't have to be TF. This can be any temperature you want, right? So you can do it in the halfway between the quench. You can say, oh, well, how much time is it going to take until it reaches 700, and you can find the time there. So it's up to you. Back to my question, guys. Which area is this? Which area? The area of the rod, right? So the surface area of the rod, which in this case is going to be what?
Don't we have the length and the diameter?
We do. We can calculate it, right? The reason why I'm asking you guys is because of the following, right? If the rod is very, very long, you can say the surface area is only going to be this guy here, and that's going to be fine. If the rod is not that long, then we need to consider also this area here and this one that we can't see over here. Okay, so there's two ways you can calculate this area. You can say the area is, let me put in two different colors, one in green. So you can say the area of this rod, AR, will be just 2 pi r times L. so that you're saying just consider this one here. Or you can say the area of this rod is going to be 2 pi RL plus 2 times pi r squared. Yeah, you can do both. Both will be acceptable in terms of, answer, question, all that thing. Which one you're going to choose depends again on the level of precision. I'm going to give you the result for both. So for the sake of plugging numbers in here, let me just plug the simple one for now. So 2 pi times the radius, 225 times 10 to the minus 3 meters, times the length, which is 2. Times the length, which is 2. Now, natural log of final temperature, 850. T infinity, 40? Yeah, 40. 850. Final initial one. I flipped this. Did I flip it? Yeah. Initial. No, that's right. Final initial. What am I doing? Sorry. Final temperature is 95, right? It's not 850. Initial temperature is 850. And this is 40. Cool. So can you guys please plug the numbers in and see what you get here?
Correct. Okay. And what I'm saying is, which one should we use? Because there's only one correct answer. Is that correct?
No, there's only one correct answer. If you say, oh, the length of the rod is so much greater than the diameters, therefore I'm disconsidering this, that's fine. It's more important to understand what the student, like the trail of thought of the student, than actually the final number per se. 254 here. Is it seconds?
Yeah.
Okay.
It's gonna be seconds, right? Yeah.
Did you check the units?
I didn't know my calculator.
Yeah, watch out. Okay, you're correct, but just watch out. You need to be sure of that. Okay, you want to be sure of that. We're gonna check the units in just a second. Pi 2 pi r pi 2. Okay. What about the second one? I think you can back me up afterwards, but I think it's going to be 251 seconds. Okay, so I just did the two different areas for the sake of comparison. Now, before anything else, let's check the units, okay? Because we need to be sure the units every single time. This is mass in kilograms. This is my C sub P, which is given in joules per kilograms per Kelvin. This here is my H, convective coefficient, which is given in watts per meter squared per Kelvin. What else? Then we have the area. The area, this is the area here, and this is given in meters squared because we convert it all to meters. So this guy is going to be Kelvin, kilogram, kilogram, Kelvin, Kelvin, meter squared, meter squared. This is going to be joules over watts. What is a watt?
Joules per second.
Joules per second, right? So I can convert this into joules per second. So indeed, ends up being seconds, and we can be sure of it, right? We can be sure that these answers here are in seconds. Great. So guys, we found out how long it takes under these assumptions here to go from 850 to 95 Celsius. If we consider the two tips of the rod, then it's going to take a bit less time, right? Because we have more area. But though the difference there is 3 seconds, it's not major. So you could say, you can argue both ways. You can argue, well, if we need to do this very precisely because of whatever reason, then we need to account for the area. If we're not, then the other one is fine because it's going to be 354, 353, something along those lines. I don't have the precision to take this thing out of the water as soon as I hit that time. It actually, there's a error of 0.1 or 1 seconds, I don't know, plus or minus 1 second, so therefore there's no point. So either, you can argue either way, okay? None of them are incorrect per se.